In one earlier video, we have constructed a velocity diagram for this 4-bar mechanism, right? So this is that velocity diagram, and once we construct the velocity diagram, then we know the velocity of at least 2 points in the link, okay? And using that information, I could identify the velocity of any point in the link, okay? And not only that, I could also identify what is the angular velocity of that link, okay? So those things we have identified, and that we can identify using velocity diagram, okay? And once we complete the velocity diagram, we'll be ready to do our acceleration analysis, okay? And we do that acceleration analysis by constructing acceleration diagram, okay? Now let's see how to construct the acceleration diagram. So here in velocity, we will have only one component, okay? That will be a tangential component for a hinged support or hinged kinematic pair. But in acceleration, we will have two terms, okay? We will have two terms. One is a radial component, another one is tangential component, okay? We'll see that equation once again. Where is that equation? Yes, so this one. So where point A and B are 2 points in a rigid body, okay? And we have two terms. One is this term, okay, and that term is a tangential component, and this term or this term, which is a radial component, okay? So in order to construct radial component, we require omega of that particular link, okay, that we can identify using our velocity diagram, okay? Alpha is one which has to be given, or otherwise we do not know, okay? But otherwise we know RB/A vector, and even here RB/A vector, okay? So for each point we need to construct, we will have two components. One is radial component, another one is tangential component. And once we complete our velocity analysis, we can calculate the radial component, okay? So it's a straightforward thing because we know omega from our velocity analysis. But the tangential component we do not know a priori, okay? We will know only after we construct our acceleration diagram. And once we construct our acceleration diagram, we can calculate alpha for each link using this equation. It is as same as our calculation of omega using relative velocity. Here we are going to use the calculation of alpha using relative tangential component, okay? Tangential relative acceleration component, okay? So we will use this equation, we will see that, okay? Now for this case, okay, I have this diagram, and I need to calculate the acceleration diagram, and alpha for link 2 has been given as 0. It's been given as 0 by mentioning that this angular velocity is constant, okay? So now with that information, I could construct a radial component. First let me construct a radial component of this link, okay? Radial acceleration, okay? So that is going to be in this direction, or let me use this picture. That is going to be in this direction, okay? And the magnitude is omega square into this length, okay? Do I know omega square? Yes, I do know. I mean, it's given. Even otherwise, from this picture I can construct, okay? So with all those information, I can draw the radial component of radial acceleration component of link 2. Okay, so that will result in this one, and it's in the opposite direction of A to B because minus sign is present. Okay, and alpha is 0. Okay, so if alpha is 0, then there won't be any tangential component. Okay, and because of that, so this point itself is representing our total acceleration. Okay, total acceleration of point B, since the angular acceleration is 0, and I have mentioned that this point is B dash 2 comma B dash 3. Okay, this B dash is to represent the acceleration, not the velocity. Okay, so just to distinguish this notation to this notation, we are putting this dash. Okay, and this 2 and 3 is to represent that point B is belong to both link 2 and link 3. Okay, so now I know the acceleration of this point. Okay, now I need to identify the acceleration of this point C. So once again, from B to C we will have two components. Okay, one is radial, another one is tangential. Okay, and for radial we know the information, we know omega 3. Okay, omega of this link. Okay, that we can calculate from the velocity diagram. Okay, so which is nothing but this relative velocity divided by this length. Okay, so from that we can calculate omega, and using the formula we can calculate the radial component, which is going to be in this direction. Okay, so I have drawn this vector and marked this point as the, that vector represents A C3 slash B3. Okay, C3 slash B3, but that's a radial component. Okay, so this point. Now I need to draw the tangential component, but I do not know the tangential vector because alpha, the angular acceleration, I do not know. But what do I know? That component is going to be perpendicular to this direction. Okay, therefore what I'm going to do from here, I'm just going to draw a line, okay, which is perpendicular to this line BC. Okay, then so, and somewhere in this line I'm going to have my AC or C prime 3 or C prime 4, because that point C belongs to both link 3 and 4. Okay, so somewhere in this line it's going to be that C3 prime. Okay, now let's see the point C from D. Okay, and what is the acceleration of D? The acceleration of D is going to be 0. Okay, now if I observe from here in link 4, the point C is going to have two components. One is radial component, another one is tangential component. To calculate the radial component, I need to know the angular velocity of this link 4, and that I can achieve from this information. Okay, so I could construct the radial component of this acceleration. Okay, so that is this vector. Okay, so if you see, it's been mentioned as a C4 slash D4, because right now we are dealing link 4, so D and C belongs to link 4. Okay, fine. Now I know this point, and from this point, to know the tangential component, I require to know the angular acceleration of link 4, but I do not know. So the only information which I know is it's going to be perpendicular to this line. Okay, so from this point I'm going to draw a perpendicular line with respect to this. Okay, and when this line and the line which I have drawn from here meet, and that will meet at this point, okay, and that particular point represents the acceleration, the total acceleration of point C. Okay, now, so once I know all these things, I could easily calculate the acceleration of point E as well. Okay, so for that, first I have to identify the angular. Okay, once again, if I see from link 3, the relative acceleration between point B and E, will have two components. One is radial component, another one is tangential component. The radial component is omega 3 square into this distance. Okay, and I know all those information, and the direction is going to be from E to B. Okay, so that's what I have put it here. Okay, I have calculated and I have put it here. Okay, and the tangential component, well, now for that I require to know the angular acceleration. Okay, so which means I have to calculate the angular acceleration. So how to calculate the angular acceleration? So recall the result which we have discussed, the equation. So this is the relation. Okay, so do I know the acceleration of, for example, of the link, any 2 points in that link? Okay, for example, I know the relative acceleration between point B and point C, and remember, we have to take only the tangential component of that. Okay, we have to take only the tangential component of, for example, between B and C, what is the tangential component? So where is B? This is my B. Okay, and where is C? This is my C. Okay, and what is the tangential component? This is the tangential component. This vector actually represents the total component, but in that total component I have to take only the tangential component. Okay, and I have to take tangential component and divide that by the distance between B and C, and that will provide me the angular acceleration of that link. Okay, once I identify the angular acceleration of that link, then it's easy for me to calculate this vector. Okay, and that's how I construct this particular point. Okay, and if you notice, for this body, okay, this link 3, in velocity diagram we have got it as one more triangle. Okay, which are similar triangle. The only thing is it has been rotated 90 degree. Okay, from here to here there is a rotation of 90 degree in counterclockwise direction. And if we draw a line from this B, this C, and this point which is E, okay, we will get one more triangle, and which is also a similar triangle to this one. Okay, the only thing is this triangle has been rotated by 180 degree. Okay, and since it's 180 degree, it doesn't matter whether it's clockwise or counterclockwise. Okay, it's like when you do a time derivative, this triangle got rotated by 90 degree in counterclockwise direction, and once again you take a time derivative, it has got rotated 90 degree in counterclockwise direction once again. Okay, so that's how you construct an acceleration diagram, and once you construct this acceleration diagram, using this you can identify the acceleration of the angular acceleration of each link, okay, and acceleration of any point in the body. Okay, thank you.